Okay, so let's learn a little bit more about buffers. So if we have something like pure water and we add acid to it or we add a base to it, the pH is going to change significantly. If there's a buffer present in the solution, though, the buffer resists the pH change, and the pH will still change, but it'll only change a little bit. So what makes up a buffer? A buffer is a solution containing significant amounts of a weak acid and its conjugate base. Or you could have a weak base and its conjugate acid. But you need to have both of them present in significant amounts. If you just have the weak acid or just the weak base, it's not going to have enough of its conjugate to act as a buffer. It'll be able to neutralize one, a weak acid alone would be able to neutralize base that was added, but there wouldn't be enough conjugate base there to neutralize any acid. Okay, so here's a picture. We mix a weak acid like acetic acid with its conjugate base. The conjugate base is acetate ion. So you have to have a counter ion with that. So sodium's a common one. So sodium acetate. We put both of these together and make a solution. Now we have acetate ions and we have acetic acid molecules. If you add sodium hydroxide to this, then the acetic acid will react and neutralize it. If you add acid to this, the acetate ions will react and neutralize the acids. So it's like whatever you throw at it is going to counteract that and resist pH changes. So we need to be able to identify what a buffer is. So here we have 4 choices. Which solution is a buffer? Well, what are we looking for? A weak base and its conjugate acid, or a weak acid and its conjugate base. Well, let's start up here. Is HNO2 a weak acid? Yeah, that's a weak acid. How about HCl? What's that? That's a strong acid. So here we have a weak acid and a strong acid. So that's not going to work. Can't talk today. Oh, purple. Life is very surprising to me sometimes. Here we have HNO3. What kind of an acid is that? That's a strong acid. And over here, we have the salt of its conjugate base, but that's not going to work because it's a strong acid. So that's not going to work. Here we have a weak acid and sodium chloride. This is not related to this at all. So that's not going to work. Here we have weak acid, and what's this? That's the conjugate base. And because when HNO2 ionizes, it forms hydrogen ion and nitrite ion. This is the conjugate base. Okay, so our last choice there, D, that's going to be a buffer solution. We have equal concentrations. We have significant amounts of both, the weak acid and its conjugate base. Any questions? How do we calculate the pH of a buffer solution? Well, let's look at that. Let's look at this solution here. We've got acetic acid and sodium acetate, and we've got 0.1 mole per liter of both of them. So we've got 0.1 moles per liter of this one and 0.1 mole per liter of that one, and we're trying to figure out what the hydrogen ion is. So we could do this. And we could figure this out using an ice table, right? We could say, well, this is the initial, and the water we don't need to worry about. The H3O, we'd say, well, that's 0 to start with. And then we'd need the equilibrium constant, the acid dissociation constant for this, and then we could figure it out, right? The presence of this acetate is going to cause the acetic acid to ionize even less than it normally would. Normally, if you had 0.1 molar of this, it would go over here and it would ionize. But now, because we already have a lot of the acetate over here, that's going to cause the equilibrium to be more to the left. It's called the common ion effect. So when this ionizes, it forms these two things. If we add a common ion to this, then it inhibits the ionization of the acid. So we have a less acidic solution than if we just had acetic acid present. Who these people are that keep texting me? Okay, so let's do a calculation. Calculate the pH of a buffer solution that's 0.2 molar in acetic acid and 0.1 molar in sodium acetate. So we've got our acetic acid, and that's going to ionize to form hydrogen ion and acetate ion. And so our initial concentrations are 0.2 for the acetic acid and 0.1 for the acetate ion. And we're going to say that the hydrogen ion concentration is approximately 0. It's going to be 10 to the minus 7, but that's too small to be important. We're going to look at the change and what the equilibrium concentrations would be. It's the same stuff we were doing in chapter 16. So this reaction is going to go in the forward direction, and so we're going to lose some amount X from the acid. We're going to gain X in the hydrogen ion, and we're going to gain X for the acetate ion. So we get 0.20 minus X, and we've got X, and 0.10 plus X. We're given the Ka for acetic acid, 1.8 times 10 to the minus 5th. And so that's going to equal the concentration of the products divided by the concentration of the reactant. All the coefficients are 1, so we don't have any squares or anything like that. So what is the approximation that we've been using to solve problems like this more easily? X is small. So let's give that a shot. So if X is small, that means that when we're adding or subtracting X, it's just really not mattering. And so we're just going to leave those guys out. So X is small, tells us that X would be equal to 0.2 over 0.1 times Ka. So 3.6 times 10 to the minus 5. You should always double check that that is small. Here we've got this, we're adding it to 0.1, we're subtracting it from 0.2. You're going to get two different results there, right? We want to look for the one that's going to give us the largest percentage, because if that one is under 5, then we're good. So I'm going to take this and divide it by 0.1 and make that into a percentage, and 0.036%. Yeah, X is definitely small. So for this ice table, my hydrogen ion concentration is equal to X. So that's 3.6 times 10 to the minus 5 So then the question was, what's the pH? So the pH is the negative log of that, 1.44. It's acidic, yeah. And that should make sense because we've got twice as much acid as we have of the conjugate base. Any questions about that one? That's a good question. What happened to the sodium ion? The sodium ion is a spectator. So I didn't write it in there. So sodium acetate is an ionic compound, right? So that's going to dissociate completely. And I'm going to get 0.1 molar sodium ions and 0.1 molar acetate ions. When I look at my ionization of acetic acid, I'm interested in the concentration of the acetate ions. The sodium doesn't play into that at all. If there was potassium or something, that wouldn't affect it either. Does that help? Good question. Anybody else have a question? So, yeah. You're getting 4.4.
That's what I got too.
Okay, well, you guys have to tell me this.
Well, I kept checking my math just to make sure it wasn't in my math because it's not what it is.
You know what I did is I took the pH of the percentage instead of the concentration. Because looking at this, -5, it should be 4 something. So, yeah, my bad. Is that better? It's 4.44. Mrs. K screwed up again. Thank you. Thank you for telling me, because otherwise it goes out there onto YouTube and the wrongness just goes and goes and goes.
Well, I just figured there was like a step in between that I missed trying
No.
to do math, and I was like,
No, I was taking a shortcut on my calculator, and that wasn't a good idea. Yeah.
I just immediately got 1.74.
Okay. Let's look at this one. We can derive an equation that relates the pH of a buffer solution to the initial concentrations of the components, the conjugate acid and the base, or vice versa. Okay, so what are we going to do here? Well, here we have an equation representing the ionization of this weak acid. And we know that Ka is going to be equal to hydronium ion concentration times the times the ion concentration here, the conjugate base, divided by the concentration of the acid. Okay with that? What we're trying to figure out is how does the pH relate to these other things? So the pH is going to be related to the hydronium ion concentration. So let's separate the hydronium ion concentration. So I'm going to rearrange this equation so that I get the hydronium ion concentration is going to be equal to Ka times Ha over A minus. I took the denominator here and I brought it up, took the numerator and put it down, and then I wrote it backwards. So I've got hydronium ion concentration in terms of the components of my buffer and Ka, but I want pH. pH is the negative log of the hydronium ion concentration. So I'm going to take the negative log of H3O plus. If I do that, then I have to take the negative log of the other side as well. So the negative log of things that are multiplied would be the negative log of one plus the negative log of the other. So negative log of Ka plus negative log of HA over A minus. Okay? So negative log of H3O plus, that's pH, right? Negative log of Ka is the pKa. And then what do we do with this business? Well, negatives are kind of icky. So if I want to make this a positive, what I do is I invert the fraction. So this part right here is equal to positive the log of A minus over HA. So I took that, I inverted the fraction so I could get rid of this negative sign. It looks like hog. Doesn't it look like hog? It's not hog, it's plus log. This is the Henderson-Hasselbalch equation. If we know the concentrations of the weak acid and its conjugate base, and we know the Ka of that weak acid, we don't have to set up a nice table. We can use this equation and calculate the pH. So there it is typed out. What I like about this is everything seems to be the products over the reactants, right? Actually, let me go back here. So here we have the product, A minus is the product divided by the reactant. And so that helps me to remember which one goes on top. Yeah, we got rid of the negative and made it this way, but I don't know why they did that, but in my mind we do that, because then it's easier to remember. Having issues here. This equation, though, only works when x is small. So you have to have the x is small approximation being valid, and that's going to happen when your initial concentrations are not too small, and your K is fairly small. So the acid concentration, the base concentration, should be greater than 100 to 1,000 times larger than Ka. So if your concentrations are the same as Ka, X is not going to be small and it's not going to work.
So what would you use instead?
So if X is small doesn't work, then you use the equilibrium approach, or you make the ice table. And then you're going to have to plug it into your solver or use the quadratic equation or something. Yeah?
You said it will be X is small when the initial concentration isn't small and when the some value is...
Yeah, so this didn't break across this line very nicely. So we want the acid concentration and the base concentration. Those need to be larger than Ka. And they should be like 100 times larger or 1,000 times larger. Okay, so it's not just, twice as big isn't good enough. 10 times as big isn't good enough. They need to be significantly larger, which is the case most of the time. Okay, so we're going to calculate the pH of a buffer solution. We're going to do both methods. We're going to do the equilibrium problem, and we're going to use the Henderson-Hasselbalch equation. So calculate the pH of a solution that is 0.25 molar in hydrocyanic acid and 0.170 molar in potassium cyanide. So this is our weak acid. The cyanide ion is the conjugate base. It's an ionic compound. It will ionize completely, and so we're just going to ignore the potassium ion. So my chemical equation here, I've got HCN, and that's going to ionize and form hydrogen ion and cyanide ion. You can write HCN plus H2O is in equilibrium with hydronium ion plus cyanide ion. That's what's actually happening, but this is less writing and it's easier to look at, in my opinion. So then we're going to do an ice table, do the equilibrium approach first. So initial concentrations. So the HCN concentration is 0.250. And the cyanide concentration is going to be 0.170. And we're going to say that the initial hydrogen ion is about 0. Then we go with our changes. We're going to lose X of our reactant and gain X in our products. So we end up with 0.250 minus X and 0.170 plus X. We're given Ka there is 4.9 times 10 to the minus 10. And that's going to equal X times 0.170 plus X divided by 0.250 minus X. And then we do X's small approximation, right? So we're going to say, well, if those are small, we can just disregard those. And so X is going to be 4.9 times 10 to the minus 10 times 0.25 divided by 0.17. So X equals 7.2 times 10 to the minus 10. Is X small? Yeah, it's really small. I'm not even going to bother checking that one. That's crazy small. We're trying to find the pH. So that is equal to our hydrogen ion concentration. So then we want the negative log, I'm not going to take a shortcut this time, of 7.2 times 10 to the minus 10. pH is 9.14. That's the equilibrium approach. That always works. Now, sometimes you can't use the X is small approach and you actually have to solve this, but it still works. Henderson-Hasselbalch equation only works if X is small. We did determine that X was small over here. So over here, we're going to use the other approach using the equation pH equals pKa plus the log of the base concentration over the acid concentration. This is the base, that's the acid. So pH is going to equal pKa, which is 9.31, plus the log of the base concentration, 170, divided by the acid concentration. We've got 9.31 plus base 10 log of 0.17 divided by 0.25. What do you know? Same answer. Any questions? So buffers resist change, but they do change, the pH will change a little bit. So how do we figure out what the change is going to be? We need to do two things. So first of all, we need to look at stoichiometry and calculate how the addition of acid or base changes the relative amounts. And then we're going to do an equilibrium calculation and calculate the pH based on those new amounts. So here's an example. We have 1 liter of buffer. It's 0.1 molar in both the acid and the conjugate base. We're supposed to calculate the pH after adding 0.025 moles of strong acid. So what we're going to do is we're going to find out how adding that acid is going to change the relative amounts. This is not an ice table. We're just looking at stoichiometry here. So we're starting out, before we added the stuff, we're saying there's essentially 0 of the hydrogen ion. We have 0.1 moles per liter of the A minus and 0.1 of the HA. Notice what we're doing here is we're working with amounts in moles because the stoichiometry needs to be moles. We can't really do concentrations. It gets ugly. So then the problem tells us we're adding this much strong acid. 0.025 moles of strong acid is being added. So we're going to assume that this is going to react completely, so that this 0.025 is going to react with the A minus. So we're going to end up with 0.075 moles of A minus, and that's going to form more of the HA. Does that make sense? It's not an ice table, but in many ways it is like an ice table. It's just not an equilibrium thing.
Just a quick question.
Mm-hmm.
So why are you adding the 0.025 to the H plus and not to the strong acid? The HA?
Well, this is the weak acid.
Oh, the weak acid. That's right.
Yeah, this is the weak acid. The strong acid will dissociate completely, and it'll give me 0.025 moles of H plus. Excellent question. Okay, so the strong acid goes in here, and we're going to say, well, that's going to react with my base here and form more weak acid. So we're going to assume that that reaction just happens completely, and so this is going to give us new starting amounts so that we can calculate the equilibrium concentrations. This is a lot like that problem, the last problem on worksheet, the roots of equation worksheet, where they said, well, here's your equilibrium, and now what if you add this many moles of this and this? Students freak out. That's what happens. So now we've got our new starting amounts for our equilibrium calculation. So we're starting with 0.125 of the HA, approximately 0 of the hydronium, and 0.075 of the A minus. It's from the previous slide. Then we look at how is this going to change, and we do our equilibrium calculation. You can do it either way. You can, put that into the equation and calculate using x is small, or you can use the Henderson-Hasselbalch equation. So we can do these calculations in moles because the volumes are the same. The equilibrium constant, the Ka, does use molarity, doesn't use moles. But in this solution where the volumes are all the same, the volumes are going to cancel out. And so that's why we can just stay with moles. What if we add strong base to the buffer? So here we have our initial concentrations or initial molar amounts of HA and A minus. And now we're going to add some hydroxide ion, 0.025 moles of hydroxide ion. Well, what's that going to do? That's going to react with the acid. It's going to cause the acid to go down in amount and cause the conjugate base to go up. And so then we're going to look at these amounts and do the rest of the calculation. So in summary, if we add strong acid to a buffer, it's going to convert a stoichiometric amount of base to the conjugate acid. It's going to create more acid. The pH is going to go down. If we add base to the buffer, the pH is going to go up. And that should make sense, because if you add base to something, the pH goes up, right? What the buffer does is it limits how much it goes up. So here we have our starting situation where we have equal concentrations of the weak acid and the conjugate base. If we add hydrogen ion to this, if we add strong acid to this, the acid reacts with the conjugate base. So we'll have less conjugate base and more of the weak acid. If we add hydroxide to our buffer, it's going to react with the acid, the weak acid, and cause an increase in the amount of the conjugate base. Does that make sense? So let's calculate the pH change in a buffer solution. So here we have a 1 liter buffer. We've got 0.1 molar acetic acid and 0.1 molar sodium acetate. So the initial concentrations are equal. When the initial concentrations are equal, we've got the pH equals pKa plus the log of 1. The log of 1 is 0. So pKa and pH are the same. So we don't have to do a calculation for the initial pH. We know what it is. But we're asked to calculate the new pH after we add some sodium hydroxide. So the first thing we're going to do is look at stoichiometry. And so we've got hydroxide ion. And what's that going to react with? The acid, the acetic acid. So that's going to react with the HC2H3O2. And what's it going to make? Water and acetate ion. Right? So at the beginning, before we add sodium hydroxide, we've got 0.1 moles of the acetic acid, and we have 0.1 moles of the acetate ion. We have essentially 0 of the hydroxide. We're told we're adding 0.015 moles of sodium hydroxide. That ionizes, dissociates completely. We don't need to think about the sodium. We've added 0.015 moles of hydroxide ion. So we're adding that in. What's going to happen? Well, this is going to react with the acid. And we're going to assume that it all reacts. So if all of this reacts, we're going to end up with approximately 0 again. And we've got this 0.1 minus the 0.015. Should be able to do that in my head, but my head's not working very well. 0.085. When 0.015 of this reacts, it'll react with 0.10515 of this, and it'll make an additional 0.015 of that. And so we're going to end up with 0.115 moles of acetate. Okay? Now we're going to do the ice table. So in the ice table, we want to look at the dissociation or the ionization of the weak acid. So we're going to look at HC2H3O2 ionizing, forming H plus and acetate. So initial is what we determined from our little stoichiometry calculation here. So the acid would have 0.085 moles. And the acetate is 0.115 moles. Hydrogen ion is essentially 0. We got our change, so we're going to be minus x plus x plus x. So at equilibrium, 0.085 minus x, x, 0.115 plus x. So we have 1.8 times 10 to the minus 5 is going to equal these guys. If we use the x is small approximation, we get 1.8 times 10 to the minus 5 times 0.085 divided by 0.115. 1.3 times 10 to the minus 5. So does that qualify as x is small? Yeah, it does. That ends up being 0.02%. Plenty small. Our H plus concentration is equal to our x. So then we can calculate the pH of this new solution. Negative log of 1.3 times 10 to the minus 5, 4.87. I'm sorry, 4.89. Why was 6 afraid of 7? Because 7, 8, 9. The Yoda one, the Yoda one is good too, but I can never get it right, so I'm not going to try. So could we have used the Henderson-Hasselbalch equation here? Yeah. Let's try it. So pH equals pKa plus log of base over acid, abbreviating there. What's the pKa? It's 4.74. Now, the concentrations we want to use here are the ones that we figured out after we did the stoichiometry of the addition. So the base is going to be 0.115, and the acid is going to be 0.085. 4.74 plus log of 0.115 divided by 0.085. 4.87. Should we be uptight about the difference between the 7 and the 9?
Could be a rounding error.
It's probably due to a rounding error. Because when I get the actual x It was actually 1.3304. So negative log, good grief. It's a mess. Negative log of 1.3304 times 10 to the minus 5 is 4.876. Which does round up to 4.88, but still. The last significant figure might vary a smidge. Any questions? So you can also make a buffer by using a weak base and its conjugate acid. So something like ammonia and ammonium chloride. The calculations are going to be very similar. But if we want to use the Henderson-Hasselbalch equation, we need to use Ka, not Kb, right? So we learned in a previous chapter that Ka times Kb equals 1 times 10 to the minus 14. This is also true. pKa plus pKb equals 14. It's the same relationship as pH and pOH. So if you know one, you can find the other one fairly simply. So here's illustration for the weak base buffer. We've got ammonia and ammonium chloride. So we have the base present and its conjugate acid present. So again, it can neutralize what's thrown at it, whether it's acid or base. Calculate the pH of a 1 liter. Oh, I know what I wanted to mention. Let's go back to this one real quick. I lost all my writing, but it's okay. When we were calculating X and using moles, that was the moles of hydrogen ion. You need to be careful. That worked here because we had a liter of the solution. If it was something else and you did that calculation, you end up with moles. You need to be a little bit careful. So just a word of warning. Okay, we're going to calculate the pH of this weak base buffer solution. And we're going to use the Henderson-Hasselbalch equation. Okay, so we've got 0.50 molar NH3, and we've got 0.20 molar ammonium ion. Well, that's not really how I want to start. Start over. Let's, so we've got those concentrations, and then we're adding sodium hydroxide to this. So we need to do some stoichiometry before we can do the Henderson-Hasselbalch equation. So we're going to add sodium hydroxide. Oops. The sodium doesn't matter. I'm just going to do, just the hydroxide. So we're adding hydroxide. What's that going to react with? The ammonium ion or the ammonia? It's going to react with ammonium, because that's the acid. And that's going to form ammonia plus water. So before we add anything, here we need to look at moles. So we're going to have 0 moles of hydroxide, approximately. We've got 1 liter of this solution. We've got 0.2 moles, 0.20 moles of the ammonium ion, and we have 0.5 moles of ammonium. And then we're adding 0.010 moles of hydroxide ion. So this is going to react with the ammonium ion, right? All of this is going to react. So after that reacts, we're back to approximately 0 for that. We're going to lose 0.01 moles of that. Right? So we'll end up with 0.19. Did I do that right? Moles of ammonium. And then we're forming an additional 0.01 moles of the ammonia. Okay? Now we can use the equation. So the equation says pH equals pKa plus the log of the base. Here the base is the ammonia divided by the acid but we have to use the Ka. They gave us Kb. pKa will be 14 minus pKb. .25, thank you. So the pH will equal the pKa plus the log. So we've got ammonia is 0.51 and the ammonium is 0.19. 9.25 plus log of 0.1 divided by 0.49. 0.51 divided by 9.27. It's actually saying 9.2673. Any questions? Okay, so I wrote it out here correctly, but I put it into my calculator wrong. So let's get rid of this. I divided by 0.49 instead of 0.19. I'm not sure why I did that, but I did it. 9.678, which would round to 9.68 for the pH. Does that look better? Yeah, thanks for pointing that out.